Alright, right now we're working on rolling motion and moment of inertia. And we have a ball on a slope and it's going to roll down the slope. So we're asked to use torque to find the translational acceleration and the velocity of the ball at the end of the slope. Whenever we have a problem like this, we're going to start using Newton's second law for rotation, and we're going to draw a free body diagram. And recall that in this free body diagram, the friction is extended away from the center of mass of the object, so it's acting at a radius. All of the other forces are acting through the center of mass and do not contribute to torque. So we take our free body diagram and we resolve our forces into the x and y direction with the x direction down the slope. Using our sum of the torque equation, we've got R times F is the torque equals I alpha, the moment of inertia times the angular acceleration. Keeping in mind that the angular acceleration is just equal to the tangential acceleration over R. So we'll make that substitution right now. Then we do the sum of the force equation. And when we look at the sum of the force equation and write out our torque equation below it, we can see that the R's cancel out in this equation, and then we can substitute friction into the Newton's second law force equation. And we get mg sine theta minus 2.5 mat equals mat. Solving for the acceleration, 5/7 g sine theta is the translational acceleration. We could have substituted translational acceleration in the moment of inertia, in the force equation and solve for the angular acceleration, but that wasn't required in this problem. So we solve for this, and to find the velocity, now we're just left with the kinematics equation because it's rolling down 2.5 meters and accelerating at 3.5 meters per second squared. So the V final squared equation is the best one to use at this point. There are some other choices, and we can solve. It's 4.18 meters per second. So we find both the answers using Newton's second law. If we go on and look at energy concepts, we've got the same problem, but we're going to use energy to find first the velocity and then the acceleration of the ball. Now keep in mind that energy, conservation of energy, says the initial energy is equal to the final energy. The initial energy is the ball just has gravitational potential, and since it's rolling, it has translational and rotational kinetic energy. Translational is 1/2 mv squared, and rotational is 1/2 I omega squared. And omega is just V over R, so we get mgl sine theta equals 1/2 mv squared plus 1/2 2/5 m r squared times velocity over r, and that whole quantity squared. And then the m's cancel out and our r's cancel out. This is an interesting function, as we find that the mass of the ball doesn't matter, nor does the radius of the ball matter. The shape matters. The distribution of mass in the moment of inertia matters. But the actual size and mass of the ball falls out of the equation. So we solve, and what we're going to get is gl sine theta, which is our gravitational potential, equals 1/2 v squared plus 2/10 v squared. Solving for velocity, we get the square root of 10 over 7 gl sine theta. And then we're going to just solve this equation, plug and chug, and then we're going to use our same kinematics equation, but this time solve for the acceleration. So we've got a 4.18 meters per second is our final velocity. And using the same equation to solve for acceleration, we find the acceleration is 3.5 meters per second squared. We get the same exact answer, solving a little differently. but energy, whether we work with energy or torque, we end up with the same solution. Thank you very much. Hope this was helpful.